be connected. And you also have to specify the footprint of each device. Okay, so let me show you what I mean by a footprint. You can pick up any component, and if I remember, let's see if I can still remember how to do this. There we go. Okay, so this is basically how you look at the details of a particular symbol on the circuit board. Most components have at least these three attributes. The first attribute is the device. The device specifies what type of device we are dealing with. A diode is one device, a capacitor is a device, the ATmega128, the MCU, is a device. So the device will specify how many pins it has, and what it is used for, and what diagram should be displayed as a symbol. The second one is a reference designator. It is a unique name of the component on the schematic. In other words, there's only one D18 in this case. It is kind of like a variable name, except this one is automatically generated. Okay, because a human cannot easily keep track of all the capacitors in use on its PCB. So the computer or the schematic capture program can automatically assign numbers to all these components, so they're all unique. The last one, or the footprint, is actually the most important one, because when we need to transition from a schematic capture to a PCB layout, we need to know how does it look like on the actual PCB. In this case, I made this component. It's called Mini2-F4-B, which is referring to the data sheet, because each manufacturer makes, a certain type of proprietary footprints, and this one is one of those proprietary footprints, which is basically the shape and the size of the pads on the PCB that you will solder the component onto. Okay, so this is where the logical representation has a representation of the physical shape of the actual device. Are there any questions at this point? No questions? Okay. If there are no questions, I will kind of switch gear to another program. The other program is called PCB because it is used for PCB layout and design. And I will show you the PCB design of the same board, but this time it is not a schematic capture anymore. This time it is actually a printed circuit board. And it doesn't want to do the full screen. That's interesting. It does not understand how big the screen is. Okay, so this is the actual printed circuit board. What appears to be red is on the front. What appears to be blue is on the back. In other words, this is what we call a two-layer board. We have the top and the bottom layer for routing purposes. You can have circuit boards that have like 16 layers, or possibly even more. But when you have a 16-layer board, it will cost you more than a few $100 to get one single prototype. Okay, this one, cost about $100 for two prototypes, which is actually not too bad. So in this case, if you zoom in a little bit more, let me just go zoom into one particular component, and let's pick the processor here. So this big square here is basically the processor, or the footprint of the processor. Each one of those, gray pads or big rectangles represents a pad where you solder a pin of the component onto. When you have a board like this, it starts off with what we call a rat's nest, which are basically lines that fly all over the place, they crisscross and whatnot. But you cannot have copper to crisscross without actually making electrical contact. So one of the most challenging part of designing a PCB is how do you route these actual copper lines so they do not overlap each other. and that's not easy. I mean that takes a lot of time to do. So in this case, this board is hand routed, which means the auto router was not used to route the board. Everything was done by hand. I always try to do it by hand first. If I cannot do it by hand, then I'll try the auto router. Question?
Did it come with eyelets, everything, like good to go, solder ready, prototype?
Yep.
So $50 a board.
$50 a board, but most of that is actually the setup cost. The setup cost is about $60, and then they charge you a per square inch cost, but the per square inch cost is really about $20-$30, per board. So this board is not expensive to make. For that price, you also get a conformal coating and the silk screen, so it looks really professional. It has the green, top, and also the white lines and the white text on it. So when I specify, like here, when I specify R1, that actually appears in white on top of the green conformal coating or solder mask. It looks really good. It really looks good. You can also turn on and off these components, or at least you can select which one you want to see. In other words, if you just want to look at the traces on the top layer and you don't care about the rest, you can turn off these things one by one until you only see just the copper on the top. If you also want to take a look at the pins on the top, you can turn that on. So this gives you an idea of what it looks like without the clutter of the rest of the layers. Most commercial PCB layout software will give you, depending on how much you pay, they will limit the size of the board as well as the number of layers that you can deal with. This is open source. It is completely open. There's no limitation to begin with. You can design a PCB with 16 layers and up to like 2 feet by 2 feet if you want to. That's a huge board, by the way. 2 feet by 2 feet is going to be expensive.
Name of software's PCB?
Yep.
Really?
The name of the software is just PCB. And this is open source. I don't know whether you can find it in Windows, but this is in Linux. If you have a Linux box... Sorry? If you want to look this up, you don't want to look up the name PCB or G-Scheme, because they are components inside one bigger package. What you want to look up is GEDA. GEDA. So if you look up GEDA, go to their homepage. Basically, GEDA stands for GPL Electronic Design Automation Tools. They are not professional tools. If you are a commercial company, you probably want to use something a little more expensive, because in the end it's worth the time and the money. But if you're just a hobbyist or have a small consulting job, this is not a bad way to get started, because it's all free. The software is free. That was my phone, sorry. So are there any questions about PCB layout and stuff like that? How many people are interested in the electronic side of stuff? Computers, embedded controllers, kind of. Getting interested? You probably want to take an electronic class. I don't know the prerequisite of the class that talks about resistance, voltages, capacitance, and whatnot. That's probably a good basic class to take. Because to design a PCB, you really need to understand a lot of that stuff. Even the width of a trace. Let me switch back to the PCB here and zoom out. You can see that some traces are really thick, like this one here is really thick. There are ones that are even thicker. Let me slide it up so you can see that. Come on. Nope, doesn't want it. Okay, you can see that these traces are really thick. These traces have to power up a lighter. A lighter that is powered from a 12-volt source. So we are pumping easily 8 to 10 amps through these traces. And that's why they're really thick, because they have to carry a lot of current. The other traces, like the whole bunch, all the way over here, they're really thin because they are only carrying logical signals, and we are talking about a small fraction of a milliamp here. So any trace is fine for that purpose. But until you have taken a physics class or an electronic class that explains resistance, current, voltage, and stuff like that, it's really hard to kind of get an idea of how thick of a trace you should use where on the circuit board. I teach micromouse, or I taught micromouse. I had taught that class for about 13 or 14 years at UC Davis, and the micromouse class is a senior year design class. So we are talking about people who are about to graduate as electrical engineers from UC Davis, and guess what? They forget about the thickness of the traces also. And because they design robots that have motors that can potentially draw a lot of current, sometimes you can see the entire trace disappear because it got so hot. It just burns itself up and it just disappears from the circuit board. So lots and lots of interesting things that you have to remember and also understand when you design the circuit board. It's not just the logical connections. When you actually route the board, you have to pay attention to all the other details that has to do with the physics of electricity instead of the logic of the design. Any questions? I mean, does the club as a whole want to design something like this? It's good experience for those who want to do it, but I can see that not everybody in the club may want to do something like this. So it's going to be like a sub-project that a few people will work on. And I don't want to waste the time of everyone when only like a few people are truly interested. So it's up to you guys to decide where you want to go. Do you want to continue the workshop? Do you want to switch to some other topic? Because the software running on this controller is also kind of interesting. It's C. It's plain old C, except it has to deal with interrupts. Now, when you have to deal with interrupts, it just throws in, it just throws a wrench into your normal thinking of, how to debug a program. Because interrupts are asynchronous to the execution of the program. You cannot anticipate when the interrupt will happen. So that means when you have a bug in an ISR or something that has to do with an ISR, the symptom may show up once a year. It may show up once a month. It may show up randomly, and each time it shows up, it can be a different symptom. So debugging that sort of bug is interesting. Can be extremely frustrating too, because the client will report and say, oh, in the field it's failing, it failed like this, and then you hear nothing back for another 2 years. And when you try to reproduce the problem, it never happens. So the software aspect of something like this is also interesting. Even with a 16 megahertz processor with only 128 kilobytes, not mega, kilobytes of space for the program space, you can still fit a multitasking kernel in it. Multitasking with time slicing and all that stuff. And the kernel that I wrote has a 2 kilobyte footprint, so it doesn't take up much space at all. So you can do all sorts of stuff when you have that much control over the hardware, because everything is under your control. There's no operating system whatsoever. There's no concept of a file. There's no concept of an operating system, allocating memory and whatnot. You are it. I mean, you have to do everything from scratch. So the nature of programming is entirely different when you deal with something like that. Any questions? I mean,
I think it'd be really interesting if you did, at some point, you could explain a little bit about, you were talking interrupts, and the only people that are going to know what that means if people are taking assembly or look at this stuff on the side, probably. But the way the timers go, with the interrupts and all that stuff is something you can't learn unless you take assembly. And even if you don't take assembly,
right.
But it has